are all familiar with the way intense heat can change the characteristics of various materials. Food is placed in an oven to bake. Wood is changed to charcoal when burned. Ice is converted to water when it becomes warm. This ability of heat to change or modify the physical characteristics of matter is an important part of manufacturing, since the characteristics of metal can be improved by treating them with heat in various ways. Heat treating consists of heating metal parts to a prescribed temperature, holding at that temperature for a specified time, and then cooling at a predetermined rate called quenching. Each heat treating process is designed to achieve a particular result. One type of treatment will make parts strong. Another type will make parts tough. A different kind of treatment develops great hardness. Another type can be used to develop softness. Still another improves mechanical properties such as tensile strength, yield strength, corrosion resistance, and creep rupture. The quality most often sought is strength. Although the idea of heat treating is straightforward, determining the correct combination of temperature, time, atmosphere, cooling rate, and cooling media for the properties of the metal can be highly complex. The first step in any heat treating process is cleaning. This involves removing fingerprints, oil, grease, lubricants, and other contaminants that might be on the part's surface. It is then ready for the furnace. The two most important factors in the heating process are time and temperature. It is essential that the metal be heated uniformly throughout, at the correct temperature, for the type of material and the desired results. Therefore, parts must be allowed to remain in a furnace until this occurs. An old rule of thumb is that the metal should be heated for 1 hour for each inch of diameter or thickness after the outside of the part has reached the desired temperature. This is ascertained with the use of devices called thermocouples, which are capable of measuring temperatures on part surfaces. Most of the furnaces used in heat treating are electrically heated, although some use gas or oil. Though more costly to run, electric furnaces produce no hot gases in order to create heat. These heating gases can damage part surfaces. Electric furnaces also tend to break down less often than those heated by other means. Air in the atmosphere of an electric furnace can come in contact with steel parts, however, causing oxygen to react with the iron in the steel to produce a layer of contamination in the form of complex oxides called scale, seen here, and with the carbon to lower the carbon content. Since the carbon content is what actually gives steel its hardness, lowering the carbon content makes the steel less hard. Air can be prevented from reaching the part by heating the material in a vacuum, or by introducing a mixture of gases such as hydrogen, argon, or nitrogen into the furnace. At certain temperatures, however, moisture will precipitate out of a gas. The oxygen in this moisture will then combine with iron and steel to form scale. The temperature at which this happens is called the dew point. The dew point is different for different gases. The type of gas used depends on the degree of surface contamination that can be tolerated by any subsequent machining operations. Those gases that create less scale, such as hydrogen or argon, tend to be more expensive, so are used only when necessary. The vacuum furnace is the most costly of all because of the initial investment and the close supervision required. However, since there is no contamination of part surfaces caused by gases, improved properties and lower rejection rates result, and this can compensate for the added expense. Quenching is often necessary in order to fix the changes or modifications in the metal caused by the heating. The faster the metal is cooled, the more changes will be retained in the material. The faster a steel is cooled, the harder it will usually be. The faster a non-steel is cooled, the softer it will generally be. It is advisable to use the mildest quenching media which will cool the metal with sufficient rapidity to develop the required properties. The most common media are water, oil, and air. The main determining factors are the type of metal being quenched. Different materials react in different ways. The rate of cooling desired. Each media cools at a different rate. And the size and shape of the part. Smaller sections will cool more rapidly than larger ones, and stresses can be created on certain parts if proper care is not exercised. In some cases, tempering is now necessary. Tempering involves reheating a part at a relatively low temperature, below that which would cause a change in it, usually from 350 to 1250 degrees. It is then held there for a certain period of time. This makes the metal less brittle and eliminates stresses resulting from quenching. Annealing can occur at any time. As in tempering, this involves heating the part at a relatively low temperature, usually from 1000 to 1600 degrees, and holding it there for a certain period of time. This softens the material and also relieves stresses caused by machining, forming, cold working, or welding. Several heat treating techniques are commonly used. Depending on the makeup of the metal, required characteristics must be achieved in different ways. In precipitation hardening, or aging, the part is heated to approximately 1400 degrees or lower for a period of time from 1 hour to 16 hours depending on the material. This causes complex carbides to precipitate out of the metal, creating greater hardness and lower ductility. No quenching is required. The metals involved in this process are usually high-temperature superalloys. Solid solution hardening involves heating the part at the required temperature between 1700 and 2200 degrees long enough to cause all alloying elements to go into solution. It is then quenched as rapidly as possible to keep them all in solution. This also creates greater hardness, though not as great as other techniques such as precipitation hardening and transformation hardening. It also creates greater ductility. This technique is also for high-temperature superalloys. In transformation hardening, the part is heated to the prescribed temperature needed to harden the material, usually from 1450 degrees to 2250 degrees, held at this temperature for a prescribed time, then quenched. The faster the quench, the harder the material becomes. It is then tempered at a temperature from 350 degrees or higher, depending on the hardness needed. This causes a change in the atomic structure of the material. The metals for which this technique is used are low alloy steels. A variation on transformation hardening is surface hardening. This technique hardens only the surface of the metal, whereas standard transformation hardening hardens the part all the way through. The three major types of surface hardening are induction hardening, carburizing, and nitriding. In induction hardening, the change in the metal is brought about by heating it selectively by means of heating coils which operate through electrical induction. In carburizing, low-carbon steel is heated at from 1650 to 1750 degrees in an atmosphere rich in carbon, such as propane. Carbon is absorbed into the surface, creating greater hardness. In nitriding, steel of special composition, usually containing aluminum, is heated in an atmosphere of ammonia. Nitrogen from the ammonia is absorbed into the surface, also creating greater hardness. An advantage of this process is that it requires temperatures of only 900 to 1,000 degrees, which reduces the possibility of part distortion. As we have seen, the physical properties of metal can be affected by heat. In heat treating metal, parts are heated to a prescribed temperature for a specified time and then cooled or quenched at a predetermined rate. The metal may then be reheated at a lower temperature to relieve stresses that may have been created by this process. This is called tempering. Machining stresses can also be relieved and the metal softened by heating the metal at a relatively low temperature. This is called annealing. Most furnaces are electric, though other types are in use. Various oven atmospheres are used. All but vacuum atmospheres produce contamination called scale. The type of atmosphere used depends on the degree of contamination that can be tolerated. Common heat treat techniques are precipitation hardening, solid solution hardening, and transformation hardening. A variation on transformation hardening is surface hardening. The types of surface hardening used are induction hardening, carburizing, and nitriding. The type used depends on the metal and the desired results. Heat treating, an important way of improving the properties of metals.